When we use C or C++, the following 5 types of bugs are quite common: null pointer dereference, use after free, memory leak, double free, and buffer overflow. These 5 bugs account for more than 30% of Linux kernel bugs. It's quite serious. Much work in programming language research has focused on fixing such bugs through type systems. The main goal of type system is exactly to reduce possibilities of bugs in computer program. Let us first summarize some terms and the problem statement of this work. As I mentioned in the previous slide, type systems are to address memory management problems. A type system may enforce pointer types. It can also automate memory management and does not allow double free or memory leak at the first place. It can enforce boundary checks, that is, no buffer overflow or underflow is possible. This is what is typically called memory safe. However, type-safe languages are not popular enough in network systems, especially in data planes. The main reason is the performance. Most type-safe languages rely on garbage collection that causes unexpected performance degradation. Also, due to several runtime verifications, type-safe languages are considered as slow languages. The Rust programming language introduced its first version in 2015 takes position of the type-safe languages for system programmers. It removed the garbage collection and runtime overhead using the affine type system. Thus, Rust generates binaries comparable to that of C languages in either case. Zero-cost abstraction sounds very cool, but it's not a free lunch. A affine type system that Rust is based on is actually too strict for general programs. To bypass the restrictions, we have to abandon the safety or abandon the performance. So our question is that how can we make network functions using safe Rust code which is based on the affine type system? The Rust selling point, zero-cost abstraction, came from the affine type system. Affine type system is a variation of the linear type system. I'll introduce the linear type system to explain how Rust zero-cost abstraction works. In linear type system, an object is used exactly once in the whole program. In affine type system, exactly once requirement is relaxed into at most once requirement. All variables are tracked in compile time and enables memory management without garbage collection nor smart pointers. As seen in the figure, each object follows the single program path, including variable renaming and parameter passing like this. The red and blue represent the type of the object, and the allocation code is inserted unconditionally by the compiler. I just mentioned the Rust type system is not suitable for general programs, but how about network functions? Network functions have unique characteristics that distinguish them with general programs, the flow affinity. When processing a packet, a network function refers to two kinds of shared states. One is called local state or per flow state, which is exclusively accessed by packets in specific flow. The other is called global state and accessed by any packets. Global states are mostly read and rarely updated, and local states are frequently updated by specific flows. These access patterns are directly mapped to the Rust affine type system. We can map local state into single writable reference and global state into read-only references. To apply the type system for network functions, we have to separate network functions into two parts. In parallel execution state, all RSS threads run in parallel, and they have two references: read-only reference to global state and writable reference to local state. Once we enter the parallel execution stage, verification for the references is done in compile time. So the reference used in the parallel stage does not have any runtime verifications, even for verification for read-only logs, no logs here. However, global state is somehow updated rarely. Then we enter the exclusive execution state where only a single thread is running and have writable access to both global state and local state. Now let's move into some numbers. First, for baseline comparison between C and Rust implementation, we choose the IP reassembly workload as the micro benchmark. We took Intel DPTK's IP reorder library for C implementation and compared it against our Rust implementation. The Rust implementation turns out to be 17% slower than the C implementation. That is, the performance penalty is Rust about 10 or 20%, not double or triple. Next, we implement network address translation in Rust and demonstrate even with global packet counters performance that scales with the number of cores. Let me introduce how that application is separated into the parallel execution and the exclusive execution stage. Basically, we have a large global forwarding table which has address triplet, internal source, external source, and the destination address. We would like to keep the global state in read-only mode mostly. When a new flow arrives, we allocate an external address from the local address pool and start forwarding packets in the flow. We sometimes enter global execution stage when a new flow arrives or we have regular timeouts. In the global execution stage, we apply locally allocated address to the global forwarding table, and we aggregate some statistics. We aggregate some local statistics into global statistics. We checked whether our net application and the parallel and exclusive execution stage are working well. The performance increases proportionally to the number of cores, and it saturates 4G link using 16 cores. The workload is 500 bytes synthetic UDP packets. From this work, we have learned the following. The state access pattern of network functions matches the affine type system of Rust very well. And exploiting this property, we have built a net gateway without unsafe calls nor software bypasses. Our evaluation shows that the performance scales to the number of cores, and it is fast enough to saturate the 4G link. It's quite a short presentation. Thank you. And questions?
What? You have a question? Yeah, I thought you called it something else.
Oh.
So you mentioned that there's a 70% performance gap between C and Rust. It would be interesting to know in a bit more depth what are the causes of that performance gap versus, I can imagine.
Okay, that's a very good question. The question was, what is the origin of the performance degradation of Rust comparing to C? Actually, the first one is how the age of the compiler. Rust compiler is very young, and actually the performance is very dependent on how the compiler optimization works. So ideally, there must not any performance degradation for Rust code, but we have some runtime verification that cannot be removed. For example, when we are accessing a vector structure, the boundary check code is enforced, and that causes runtime overhead for every vector access. But when we are only using the affine type system, read-only references and writable reference in specified in Rust language, then there theoretically there must not any performance degradation. As yeah.
The affine syntax is going to help you with your radar checking part. But
Yeah.
there are other type theoretic things that could help you with that. If you could, there's systems of dependent types, for instance, that will allow you to do static checking. So array bound checking will really be key feature that would
Yes.
make that performance gap. Then one could think about language extensions, more sophisticated type systems that eliminate that and potentially approach the C-level performance. But on the other hand, some other problem with Rust, like the object representations or something like that, then we'll have to think about different tactics for improving performance. So it'd be really useful to know where exactly the problems lie. To figure that out, then you could basically propose changes to your Rust that would allow higher performance programs. So, it'd be interesting to investigate the details.
Oh, okay. Yeah, so for a quick reply, so there are many ways to represent a C feature in Rust. For example, when we are going to represent a reference pointer, we can use the native Rust implementation of pointers, or we can have some software wrappers using reference counter. Then that allows Rust language to use arbitrary pointers. But that is not intended in Rust, because Rust intended a zero-cost abstraction by a affine type system. So it is better to use the affine type system more and more. But we found that the access pattern in network function really matches the affine type system of Rust. And so conclusion is that network applications are very good usage of Rust language, we think. Thank you.
Thanks. We're going to have to jump on because of time restrictions, but there's going to be plenty of time after the break to talk over posters. So thanks once again.
So your slides are, you have enough?
Yeah, sure. Thank you.
There we go. Just copy it to